The concept seems to defy every principle of conventional urban planning and civil engineering we've held for a century. A city, not sprawling outward, but contained within two insanely long, impossibly tall, perfectly parallel mirrors stretching across the desert for over 100 miles. A place with no cars, no streets, and no carbon emissions, where you could theoretically travel from one end to the other in just 20 minutes. This is the line at NEM, and when the renders first dropped, the entire architecture, engineering, and construction world had one collective, simultaneous reaction. How? How on earth do you build that? It's one thing to dream of a utopian linear city. It's another to break ground on it in one of the planet's most challenging environments. The gap between that visionary concept and physical reality is a chasm filled with some of the most profound engineering puzzles ever conceived. So, let's move past the hype and the glossy animations. Let's talk about the nuts and bolts, the concrete and steel, the logistics and the code violations that need to be rewritten. This is the story of how the line is being engineered from scratch, and it begins not with architecture, but with geology. You cannot place a city that weighs billions of tons on just any patch of ground. The site selection along the Tabuk coast of Saudi Arabia wasn't arbitrary. Extensive geotechnical surveys involving seismic tomography, core drilling hundreds of meters deep, and analysis of bedrock composition had to confirm a stable, continuous geological stratum capable of bearing the unprecedented linear load. Imagine the foundation not for a point-load skyscraper, but for a continuous, razor-thin wall of a skyscraper that runs for the length of an entire country. This demands a uniform bearing capacity rarely found in nature. Engineers are likely dealing with a combination of deep pile foundations, possibly reaching down to bedrock, and reinforced concrete rafts of a scale never before poured. The thermal expansion of materials over 170 kilometers is another nightmare. A steel beam expands about 1.2 centimeters for every 100 degrees Celsius temperature change over a 100-meter length. Scale that to 170,000 meters with the brutal diurnal temperature swings of the desert. If the entire structure were rigidly connected, it would tear itself apart. The solution? Expansion joints. But not your typical sidewalk gap. We're talking about massive, engineered joints at regular intervals, perhaps every kilometer or so. These would be complex, multi-dimensional interfaces that allow for thermal movement in the long direction, but also for seismic sway and wind deflection, all while maintaining a perfect seal for the internal environmental layer and the external mirrored cladding. They are marvels of mechanical engineering in themselves, acting as giant shock absorbers for the entire city. Now, let's talk about the structure itself. The defining image is two parallel skyscrapers, 500 meters tall, spaced 200 meters apart, with a climatic canopy connecting them at the top. This is not simply two separate buildings. They function as a single, integrated structural system. The most efficient way to resist the primary lateral loads, wind and seismic forces, is to connect these two vertical planes. The canopy is not just for shade or climate control, it is a crucial structural diaphragm. Think of it as a gigantic, continuous bridge deck sitting 500 meters in the air, tying the two parallel walls together. This creates a monumental U-shaped tube, or, more accurately, a rectangular hollow section that is incredibly stiff against bending and torsion. The wind loading analysis for this form is a computational fluid dynamics monster. Unlike a typical prismatic skyscraper that wind flows around, the line presents a sheer, continuous face. It will create unique wind patterns, downwash effects, and vortex shedding along its immense length. The structural frame within those mirrored walls likely employs a hybrid system. At its core, you'd have a robust reinforced concrete shear wall core, or more accurately, a continuous linear core wall, housing the vertical transportation and utilities. Married to this would be a megaframe of steel or composite columns and outrigger trusses that connect to the exterior facade. This exterior isn't just a curtain wall, it becomes a tube-in-tube, or D-grid system, where the mirrored facade panels are backed by a structural grid that participates in carrying gravity and lateral loads. This distributes forces efficiently and allows for the vast, column-free interior spaces promised in the renders. The construction sequencing here is where it becomes a logistics ballet on a planetary scale. You don't build 170 kilometers sequentially from one end to the other. That would take centuries. Instead, the project will be broken into dozens, perhaps hundreds of modules or precincts built simultaneously. This demands a level of supply chain orchestration that makes building the pyramids look simple. Each module needs identical or near-identical materials, millions of tons of cement, steel rebar, glass, and prefabricated facade panels. Localized gigaplants for concrete and steel fabrication have already been announced because transporting these materials by road from distant ports is economically and logistically impossible. The on-site logistics corridor, the space between the two parallel construction zones, becomes the busiest linear highway on Earth, dedicated solely to construction traffic, tower cranes, thousands of them, mobile elevating work platforms, concrete pumpers, and autonomous trucks delivering prefabricated modules. This leads us to the unsung hero of the line, the spine. In the glossy videos, you see pristine nature and communities. What you don't see is the hidden, multi-level mechanical, electrical, and plumbing cathedral running the entire length beneath the city. All the back-of-house functions of a city, the hyperloop, the freight logistics, the water pipes, the electrical substations, the waste management systems, the data servers, are to be buried in a continuous service deck. This is perhaps the most intelligent engineering decision of the entire project. By creating a dedicated, segregated infrastructure spine, you achieve several things. First, you enable 100% maintenance and upgrades without disrupting life in the main city layers above. Second, you create a secure and efficient conduit for autonomous freight delivery, meaning no garbage trucks or delivery vans ever mix with pedestrian traffic. Third, it allows for a plug-and-play utility grid, where segments can be isolated or modified. The engineering of the spine is like building a continuous, submerged subway system, utility tunnel, and data center all in one. Ventilation, fire suppression, and access for service robots within this spine are monumental design challenges in themselves. Let's discuss transportation, the feature that defines the city's function. The promise is no journey longer than 20 minutes. With a length of 170 kilometers, that implies an average speed of over 500 kilometers per hour for end-to-end travel. This is the realm of Hyperloop or maglev technology, both proven at this scale for public transit. The engineering challenge isn't just the vehicle, it's the guideway. Maintaining a near vacuum or a precisely aligned magnetic levitation track over 170 kilometers of desert, with thermal expansion and potential seismic movement, is a precision engineering task of astronomical difficulty. Stations cannot be simple platforms. They would likely be vertical transportation hubs where high-speed spine transit connects to local vertical and horizontal mobility, elevators, ascending walkways, and autonomous pods within the city layers. The integration of these systems with perfect synchronization and 0 points of failure is a control systems engineering problem that pushes the boundaries of the Internet of Things and AI coordination. Now, the mirrored facade. It's the iconic aesthetic, but it's also a colossal environmental and structural challenge. Sourcing, manufacturing, and installing enough high-performance, double-silvered low-emissivity glass with integrated photovoltaic layers to cover hundreds of square kilometers of surface area is an industry-breaking demand. Each panel must be prefabricated, often curved, with perfect reflectivity. Their structural fixing system must accommodate the building's movement, resist wind pressure and sand abrasion, and maintain a perfect seal. Cleaning and maintenance of this facade introduces another layer of complexity, likely requiring a permanent army of autonomous, robotic window cleaning drones running on vertical rails. Behind this mirror, the environmental control is what makes the city livable. The goal is a microclimate. The canopy and the building's orientation are designed to create shade and promote natural ventilation. However, in the peak of the Saudi summer, mechanical systems will be essential. The engineering of the HVAC system is unlike any other. Instead of individual building systems, you might have district cooling plants located in the service spine, pumping chilled water through a network that serves the entire linear city. Air distribution would be through underfloor or displacement systems to maintain comfort without drafts in the deep, open-plan spaces. Water is the lifeblood, and in a desert, it's the ultimate constraint. The line promises a closed-loop water system. This means massive, energy-intensive desalination plants, likely solar-powered, on the coast, with the purified water pumped through a shielded pipeline running the length of the city. Then, every drop of gray water from sinks and showers, and black water from toilets, must be captured, treated, and recycled with near 100% efficiency. The treatment plants themselves become linear facilities within the service spine. Solid waste is treated as a resource, likely through automated vacuum waste collection systems that suck trash from designated ports to centralized processing facilities for recycling or energy conversion. Finally, we must talk about the digital foundation, building information modeling. This project is impossible without a fully integrated 4D and 5D BM model. Every single component, from a structural bolt to a hyperloop carriage, exists in a federated digital twin long before it is fabricated. This model coordinates the work of tens of thousands of designers and engineers from hundreds of firms worldwide. It schedules the construction sequence, 4D, tracks the cost in real time, 5D, and will eventually manage the entire asset lifecycle. Clash detection isn't just for a few pipe collisions. It's run on entire kilometers of the city model at once to pre-resolve conflicts between the structural frame, the MEP spines, and the facade attachments. The software platforms like Revit, Navisworks, and custom-built integration platforms are pushed to their absolute limits, requiring cloud computing resources on a scale akin to major tech companies. In conclusion, engineering the line from scratch is less about a single eureka moment and more about the ruthless, systematic application of known engineering principles at a scale and integration level that has never been attempted. It's about solving a cascade of interconnected problems: geotechnical, structural, mechanical, logistical, and digital. It requires reinventing supply chains, writing new building codes for linear urban forms, and developing new construction robotics. The pro tip from megaproject engineers is this: the innovation is in the interfaces, how the structural expansion joint also seals the climate barrier, how the robotic facade cleaner also inspects the photovoltaic layer, how the digital twin of a water pipe informs the autonomous maintenance robot. The common mistake is to see it as one project. It is 1,000 major projects proceeding in parallel, linked by a single unwavering vision and a digital thread. Whether the line is fully realized as depicted, the engineering solutions developed in its attempt will irrevocably change how we think about building cities. It is a high-stakes laboratory for the future of civilization's infrastructure. If you want to dive deeper into the specific structural systems for skyscrapers like these, check out our next video on tube frame and diagrid design. And as always, if you work in AEC, comment below with the biggest engineering challenge you think they still haven't solved. Don't forget to subscribe for our deep dives into the engineering behind the world's most ambitious builds.